Alrighty, we were able to get this recording software working. So I'm just going to go through the lecture again for y'all. I know a lot of people can't attend anyway for scheduling reasons, so they rely on the lectures to be recorded. So here we go. Alright, so last semester we talked a lot about reactions and mechanisms, and we use these curved arrows to show electron movement. And we're going to do a lot more of that this semester, but this first chapter about free radicals is going to involve these other types of arrows. The fishhook style arrows that involve a single barb on the head of the arrow instead of the double barb. And those are meant to show the movement of one electron instead of two electrons. So in a case where a bond is breaking, it could break heterolytically, which we saw a lot last semester, and especially when you have different electronegativity values, the more electronegative atom might pull both electrons toward itself, and that produces often a carbocation and a leaving group that left. We saw a lot of reactions like that where the electrons both go to one side. Typically, though, when you're just using heat, or especially if light of a certain wavelength is used to break a bond, you may find much more often that it breaks homolytically, homo meaning same. So it breaks evenly or the same on both sides. And so the fishhook arrow shows one electron going to this atom and one electron going to that atom, and that produces free radicals. So since free radicals can be formed with the right amount of energy in the form of light or heat, and those can undergo a variety of reactions, we want to touch on some of those reactions and give ourselves the background necessary to understand these processes in detail. So, comparing to carbocations and carbanions, right? Carbocation is where I have an incomplete noble gas configuration. Carbanion, I have a complete noble gas configuration, but that lone pair creates a formal negative, which is a pretty harsh charge imbalance on such a small atom. A free radical doesn't create any charge, because if I calculate the formal charge of that carbon, it'll end up being 0. But it is an incomplete noble gas configuration, which is also still relatively unstable. What about the orbitals that are involved? So when we talked about carbocation, we said a carbocation involves an empty p orbital. Right, so I've got 3 things bonded to the carbon. They're all on the same plane, and this empty p orbital is perpendicular to that plane. And so this allows for the possibility of a nucleophile. We saw carbocation is a great electrophile. It very strongly attracts electrons into complete its noble gas configuration. The nucleophile can come in and start sharing electrons, and as that occurs, the head-on overlap between this usually hybridized orbital and the p orbital will hybridize into an sp3 as the overlap occurs, and that will make a new sigma bond. Carbanions already typically exist in a hybridized orbital, right? And that's because if I were to compare that to a situation where I could imagine the lone pair in a p orbital is just slightly more elongated than an sp3, and so the electron density isn't as close to the nucleus as it is on average if the electrons are in a hybridized orbital. So these hybridized orbitals allow for stronger attraction between the electron and the nuclei, and that stabilizes the negative charge of the electrons better. So usually we see carbanions in an sp3 orbital. Not always though, right? So before we look at the orbital on a free radical, let's just remind ourselves what we talked about last semester when we said that a carbanion could exist in a p orbital instead of the sp3 that's shown here. So the situation where I would have a lone pair on an atom that would be in an empty p orbital, I'm sorry, it wouldn't be empty because there'd be a lone pair in it, but the lone pair in a p orbital versus a hybridized orbital Usually the p orbital doesn't stabilize it as well, and we said that's because the p orbital is more elongated, the electrons aren't as close to the nucleus on average. But if there's a neighboring atom that also has p orbitals, maybe there's a pi bond here, CO double bond or something like that, any kind of pi bond, there are going to be p orbitals there. And so the lone pair in that case would be more stable in a p orbital than an sp3. And that's because of the resonance that can occur there. Right? So the overlapping side-by-side p orbitals allow for a molecular orbital to occur extending over multiple atoms. The more atoms involved in that, the more stabilizing the resonance is. And so stabilizing a lone pair in a p orbital through resonance is more stabilizing than it would be in the slightly more compact sp3 orbital, because in an sp3 it's localized and only able to attract to one nucleus at a time, versus in a resonance it can attract to all these nuclei, being in an extended molecular orbital covering all of them. So even though it's a carbanion, it's not always one type of orbital or the other. It depends on the situation. So when you have a free radical, there are a couple different ways you can think about that. You can think about the free radical existing in a p orbital, where the carbon is sp2 hybridized. Or if the carbon sp3 hybridizes, you can think about the free radical in an sp3 orbital. It doesn't require the larger section of that orbital always be on one side of the carbon, though. So this inversion or shifting can occur readily for free radicals, right? So normally we think of hybridized sp, sp2, or sp3 type orbital as having one larger lobe and one smaller lobe, but there's no reason why the larger lobe has to be on one side and the smaller on the other. So these two can shift or switch, and that means the radical exists just as much of its density exists above as it does below the carbon. So in essence, there's no practical difference between these two scenarios. So for the sake of simplicity, I think it's usually easier, if at least for me, to think about the free radical as being in a p orbital. And that also allows us to recognize that when the free radical is adjacent to maybe like a pi bond, the p orbitals of that pi bond can overlap side by side with the orbital the radical's in, and allow for the radical to be stabilized through resonance, just like a lone pair. And that really is important to looking at some radicals that are especially stable. So how can a free radical be stabilized? There's a few different ways it can be stabilized. We're going to look at them. So one is hyperconjugation. We talked about hyperconjugation last semester in the context of stabilizing a carbocation. So if you have a carbocation, what you're dealing with is an empty p orbital. There's no electrons there. So we can stabilize that more effectively through resonance, but it can also be stabilized through hyperconjugation. And hyperconjugation involves some sigma bond on the neighboring atom rotating into the same plane. Could be a hydrogen, could be a carbon, whatever that element is. If its sigma bond rotates into the same plane as the p orbital, then those sigma bonds can share a little bit of electron density in with the p orbital, and that helps to stabilize that p orbital, right? It's empty, it needs more electrons to balance its charge, it needs more electrons to complete its noble gas configuration. So it's not as stabilizing as resonance because the orbital overlap is not very effective, and these sigma electrons aren't really available to like shift readily. They can just donate a little bit of electron density in there, which helps to stabilize it only slightly. So the hyperconjugation is significantly stabilizing, but not nearly as much as resonance. And it's much more stabilizing if I have multiple bonds that can all rotate into that position and all donate electron density at once. So for example, if I have hydrogens there, they can't do that at all. R groups, where I have carbon bonded to hydrogen or carbon bonded to carbon, those orbitals can start to overlap with the p orbital that's empty in the case of a carbocation, or that holds one electron in the case of a free radical. So free radicals are also stabilized through hyperconjugation, just like carbocations. They don't involve any charge, but they are in complete noble gas configurations, and so shifting some electron density in there helps to get that carbon closer to complete its noble gas configuration and makes it a little bit more stable. So the more R groups there are, the more stable it is due to hyperconjugation occurring from more sides instead of just 1, 2, or in the case of a methyl, 0 hyperconjugation whatsoever. And so we showed that. And so here just is some experimental numbers that show the differences there. Right? So these are in kilocalories per mole. And what we see is a slight difference in the quantities of energy involved. And so what that means here is, let's say we'll look at the tertiary one. If we were to plot potential energy, which is the same as enthalpy, versus the reaction progress. This molecule is relatively stable. It has complete noble gas configurations, no formal charge, so it would be relatively low in energy. And if we break this bond homolytically, it'll produce a hydrogen radical and a tertiary radical. That tertiary radical will be stabilized through hyperconjugation from each one of these methyl groups. And so it doesn't require a huge amount of energy to break that. So the energy required would be large, and it's a positive value. And that's because the free radical, the tertiary radical, is significantly less stable than the tertiary structure to begin with, but the hyperconjugation helps to stabilize it. And so the energy difference there is the 97 kilojoules per mole. These other ones are just slightly larger. It's just a little bit. So hyperconjugation is not an extremely big factor. It's a minor factor, but it is significant. And if we looked at the methyl and we try to do the same thing there and break that bond, it would take more energy. And so if we looked at the methyl, it would require a higher energy to get to the methyl free radical. So the tertiary will form a free radical more often because it doesn't require as much energy, so it's favored kinetically. None of these free radicals are favored versus the full complete noble gas configuration from a thermodynamic perspective, though. And so this just basically illustrates the differences, significant but not major differences between the amount of energy required to make a tertiary free radical versus a methyl, a primary, or a secondary. So these numbers demonstrate how effective hyperconjugation is at stabilizing a free radical. We can compare that to the effect of resonance on the stabilization of our free radical. So when you're dealing with resonance, you want to remember all the things we talked about last semester. The arrows don't actually show the electron movement. The reason for that is because the electrons aren't shifting back and forth. Instead, they exist in molecular orbitals that extend over the multiple atoms. So a hybrid structure is the most correct structure. It shows, or at least has a representation for the molecular orbitals that exist. But to get to the hybrid, to recognize what elements those molecular orbitals extend over, we really need to be able to draw the individual contributors. So if you have a free radical that's allylic or adjacent to some pi system, meaning it exists as a p orbital, and its p orbital overlaps with the other p orbitals side by side, that's going to allow that side by side overlap to create extended molecular orbitals over 3 or more atoms. So to draw the other resonance contributors, you would use the fishhook arrows to show the radical moving in and joining up with one electron from the neighboring pi bond. The other electron from the neighboring pi bond moves out here, right? So you can't do this. That would create something very unreasonable. It doesn't necessarily look unreasonable, but there's a hydrogen here, right? So again, just like last semester, it's easy to make mistakes if you're not aware of where the hydrogens are in a certain area. So these patterns aren't just random. They're the only way to create alternative structures that are relatively stable or similarly stable. So with the hydrogen here, this would obviously create more than 8 valence electrons around that carbon, which you can't do. So obviously that arrow is no good. So when you're shifting electrons around in resonance, make sure you follow the same guidelines we talked about last semester. You can't break any noble gas configurations by going beyond 8 electrons for any second energy level atoms, absolutely ever. So the arrows that are already here on the slide show how to get to the other contributor. And then to draw the resonance hybrid, which is a more realistic view of what the structure actually looks like, you would draw the sigma bonds that represent the electrons that are localized and not moving around in resonance. And then each area between two carbons is a composite or average or hybrid of what those areas look like in the individual contributors. So here I've got a single bond on this side and a double bond over here. So the reality is I've got something between a single bond and a double bond, like a bond and a half. Same thing on the other side, between the other carbons. And so that dotted line helps you to recognize the molecular orbitals extending over all 3 atoms. The electrons involved in resonance are instantaneously spread out over all 3 atoms. They're not here sometimes and here other times. They're instantaneously spread out over the whole thing. And typically in resonance, previously we would have charges involved. Here we don't have charges, we have free radicals. So we want to show which atoms that free radical is spread out over. There are 3 carbon atoms here, but the free radical in the only 2 contributors I can draw exist on the end carbons. So it's the 2 end carbons that are sharing that free radical. And it's more stable to have a partial free radical than a full free radical, just like it's more stable to have a partial charge than a full formal charge. So here's another example. I've got this free radical here. It's in conjugation with this pi bond because it's p orbital. It's overlapping with the p orbitals there. So the electrons can move in the same pattern to shift the free radical over not one carbon, but 2 carbons over. And we can do the same thing here. And if we draw the structure that results from that, got a double bond here. This electron moves in and joins with that one. I'll form a double bond there. This electron swings out, form a radical. This pi bond's still here. So that's another contributor. I'll keep going all the way around the ring. So if the single electron moves in here and joins up with one of these to make a pi bond, the other electron from the pi bond can swing out there. So that forms a 4th resonance contributor with a radical at this position. And then you could imagine that radical coming up here, joining with one of the pi electrons from that pi bond, shifting the other one out there, and that goes back to the original structure. So there are 4 resonance contributors here. None of these exist. The electrons aren't shifting back and forth, but drawing each individually can help us correctly draw the hybrid. Right? In the hybrid, all the sigma bonds maintain their localized positioning, and any carbon-carbon bond in one of the structures is going to be a single bond, and the others is going to be a double. So here I've got some fraction of a bond in addition to the single bond. It's not really a single, it's not really a double, it's somewhere in between. And that's true of every one of these carbon-carbon bonds. So each one of these positions needs to have a dotted line to represent that. To complete the hybrid, we would then show which carbons the radical is shared over or spread out over. So the radical exists on carbon 1, 3, 5, and 7 in one or another of the resonance contributors. So that means instantaneously I don't have any individual atom that has the instability of a free radical, but all four of those atoms take on a small quantity of that instability. And spreading it out stabilizes the structure rather than having it concentrated in any one spot. Spreading the electrons over multiple nuclei stabilizes them as they form more attractions that way as well. So make sure you practice that skill. It's likely that you'll have to draw some kind of resonance involving radicals on one of the exams coming up. So how do we quantify the stability of resonance and compare that to the stability of hyperconjugation on a free radical? What's a bigger factor, hyperconjugation or resonance? Well, the bond dissociation energies can answer that question for us, because we see to break this bond and form a tertiary free radical that's only stabilized by hyperconjugation takes a fair amount of energy. So that means the resulting structure, the tertiary free radical, is relatively high in energy and somewhat unstable. If you do the same thing at an allylic position or a benzylic position, you form the free radical that's stabilized by resonance, and you can see significantly less energy is required to do that. So the resonance stabilizes the resulting free radical, lowering its energy, so less energy is required to get to that higher energy intermediate. It's significantly less. Right? We saw back here that the quantities were relatively minimal. It's a pretty big difference between tertiary and methyl free radical. That's a big difference in energy, and almost the same difference between the tertiary and the resonance stabilized ones. So resonance is much more stabilizing than hyperconjugation when it comes to stabilizing free radicals. Right? So even though this would form a primary free radical, the resonance stabilization makes it require way less energy to form than a typical primary free radical, which takes upwards of 100 kilocalories per mole of bonds to form. Vinyl free radicals are even less stable, though. And so the vinylic position, if you recall from OChem 1, the vinylic position is the position directly attached to an sp2 hybridized carbon involved in a pi bond of some sort. So a vinyl chloride would be a chlorine there. A vinyl radical would form if you break a CH bond and produce a free radical right on that carbon. So that takes a lot of energy. It takes more energy than a primary or a methyl. And the reason for that is because of the orbitals that are involved. And so if I have this carbon-hydrogen sigma bond, this carbon is sp2 hybridized. So an sp2 hybridized carbon has a sp2 orbital that's overlapping with the hydrogen's 1s, and the electrons in there, being that the sp2 orbital is relatively compact, those electrons, that electron density is pretty close to the carbon nucleus. So to take one of those electrons away requires its attraction to the carbon nucleus to break. And the more compact the orbital, the more strongly it's attracted, the more energy it takes to break an electron away. It's one way of thinking about it. We're also saying that, when we think about the energy, we're starting with relatively stable substances. When we form these free radicals, they're pretty unstable. So the more energy required to get there means the more unstable it is. It takes a lot of energy to get up to that really unstable point. So why is it so unstable to form a radical here? Well, it has to do with the orbital, as we said. If it's an sp2 orbital, it's more compact than an sp3. It's more compact than a p orbital. And so basically we're creating a structure that's especially unstable because there's a gap or an empty spot relatively close to the nucleus in this compact orbital. So it's unstable. It's very likely to react maybe forward or back. It's very likely to react. It's very unstable because it's a spot that's close to the nucleus, and the positive charge of that nucleus is going to be good at attracting a new electron in there. Actually, it would probably be a single electron, maybe belonging to some nucleus, to reform that sigma bond that allows the electrons to get pretty close to that nucleus and stabilizes them. So the vinylic position, not stabilized by resonance, and in fact the orbital involved makes it even less stable to try to take electrons away from that space that's pretty close to the nucleus. All right, so one difference between free radicals and carbocations, even though they have a lot of similarities in the orbitals that are involved, and the fact that they both involve an incomplete noble gas configuration. One difference is carbocations undergo rearrangement, free radicals really don't. Right, so there are two types of rearrangement we talked about carbocations undergoing last semester. There's a methyl shift or a hydride shift. In this case, it would be a methyl shift, right? We got a secondary carbocation. It's only got 2 carbon groups on either side to help stabilize it through hyperconjugation. There's no resonance to stabilize it. So if we can get into a tertiary carbocation or a resonance stabilized one, which won't be possible here, but shifting the methyl over to make a tertiary carbocation. So now there's only one methyl left on this carbon. The other methyl shifts over here, so now it's on this carbon. That creates a more stable tertiary carbocation. Right? So there's a hydrogen here, still there on that carbon. So this carbon is no longer a carbocation. Now it has 4 bonds when the methyl brings its electrons over. But now this carbon, since it lost a methyl group, only has 3 bonds, and it's a carbocation. So now it's tertiary. And so we said that happens relatively quickly. All it requires is a slight collision, and for one of the methyl group sigma bonds to rotate into the same plane as this MTP orbital and just jump over. That doesn't really happen with free radicals. With a carbocation, the methyl group can bring both its electrons over, so that just happens to happen more easily. With a free radical, the methyl group would be required to bring 1 electron over and leave 1 behind. And that requires a higher amount of energy. So we really don't ever see that occurring in significant amounts in reactions. So once you form a free radical, it's not going anywhere, at least not through this type of rearrangement. If there's resonance, it could shift to another atom. If there's another radical that comes in or a molecule that comes in and reacts with it, obviously you can form a product from that, but not the type of methyl shift or hydride shift that we would see typically with carbocations. So what type of electron movement do radicals undergo? Well, there are 6 patterns you want to be familiar with. Really, ultimately, we'll see in a minute, this comes down to 3 patterns that are reversible. So we'll outline all 6, and then we'll show how 3 are really just the reverse of the other 3. So homolytic cleavage, we already saw that's 1. It's where a sigma bond can break open, produce individual free radicals. That's obviously reversible if the radicals come back together. So typically that would favor the reactant side unless you're at a very high temperature or continue to hit it with high energy light. Another pattern is where a free radical adds across a pi bond. This is the type of pattern that's occurring in your polymerization reaction for lab 1, where the radical continues to exist at the end of the chain each time. Right? So this would, if it occurred again, it would extend the chain, and the radical would always be on the end, and another monomer could react there and add to that. And so the advantage of this is you're converting a pi bond into a sigma bond. The sigma bond is typically more stable than a pi bond due to holding the electrons closer to the nuclei. And we learned that last semester. And so that helps drive that reaction forward. However, you are combining 2 reactants to make 1 product. So entropy favors the reactant side. So if you heat that up enough, that can cause depolymerization, and as we know, an increase in temperature magnifies the entropy term in the delta G formula and shifts reactions toward the side with more entropy. Another pattern is a hydride abstraction, halogen abstraction. Hydrogen abstraction and halogen abstraction are very similar. So this is not the same as a proton transfer, just to remind you. A proton transfer is where some acid loses a proton to some base. The base uses a pair of electrons to pick up the proton, and the acid keeps both electrons behind. Right? So this is two electrons moving in pairs, and the proton is transferred because a hydrogen's nucleus is simply a proton. If it doesn't bring any electrons with it, it's the proton that's being transferred over. Halogen abstraction is different because the hydrogen actually takes one of the electrons with it. So if this X, which might represent a halogen or some other element, has a free radical, its free radical needs one more electron to form a pair, so one electron will go with the hydrogen and form a bond there, and the other will stay behind. And this would shift in equilibrium to favor whichever side has a more stable radical that forms. It can go in the reverse direction. The carbon can pick up a hydrogen, or in this case a halogen. So this halogen molecules are common in radical reactions. This could be like a Cl2 or a Br2. If the carbon has a radical, it can pick up one of these halogens. The halogen brings one electron with it, the other stays behind to produce another radical. And that's obviously reversible as well if the two halogens join together and reform the carbon radical. Step 5 here is another possible mechanism step you might see for radicals where you're eliminating something. So this is a little bit different from the elimination reactions we saw last semester. Typically last semester you'd have a leaving group and you'd have a proton antiperiplanar beta to the leaving group, right? And then you'd use some base. If it was a strong base, it would go by an E2 mechanism. It would pick up the antiperiplanar proton, electron swing in, push out the leaving group. That's how you make a pi bond. In this case, though, if I have a radical here, all that's needed is one electron to make the pi bond. So there's no leaving group. This is not a leaving group situation. A leaving group, by definition, has to take both electrons it's sharing with it. And that's not really happening here. Right? The X is breaking away from the rest of the structure, but it's not technically leaving by definition because it's not taking both electrons with it. So one electron would stay behind to join with the one that's already there to make a pi bond, and the other would go to produce the halogen. Finally, the sixth pattern involves coupling of two radicals to form a sigma bond. So this doesn't occur very often. It's very product favored when it does occur because the bond allows the electrons to exist in a molecular orbital between both atoms, attracting to both nuclei versus the atoms being independent and not having as many attractions with the electrons. Also, completing the noble gas configurations usually makes it more stable than having the incomplete noble gas configurations associated with the radicals. But in most reactions, there aren't very many of these around. Because they're so unstable, when they usually form in small amounts and then quickly react. So you don't usually build up large quantities of these, and it's rare that they would just by random chance be bouncing around a solution and find the opportunity to meet one another. It does happen, just not very often. But when they do meet, it's almost always going to lead to product formation by forming that sigma bond to stabilize the electrons. Note that most of these involve 2 or 3 fish-hook arrows. So you really do, like last semester, need to be able to draw mechanisms that are correct, and you need an arrow to show the movement of every electron. So if any electron rearranges in any way, there has to be an arrow to show that rearrangement. So this slide shows how each of those steps is the reverse of another. We said there are 6 patterns. And so each one of those patterns is a reverse of one of the other patterns, right? So the homolytic cleavage, breaking up of the bond is the same, or a reverse of the coupling of the two radicals. Hydrogen abstraction to produce a carbon-free radical. There's a reverse of that where the carbon-free radical can pick the hydrogen back up. And then the addition to a pi bond for a free radical, which produces an electron on the carbon, can be thought of as the opposite of the elimination of that halogen from the carbon to reform the pi bond. All right, so some of these steps in the context of reactions. Actually, I think I'm just going to skip over this part here. Some of these definitions are not really the best, most formal definitions of these terms, and I don't want to define things twice to get you all confused too much. So let's just move forward to looking at a specific reaction. So here's a specific reaction that involves free radical. How do I know that? Well, anytime I see HV, that's a really big clue that's going to be a radical reaction. So HV is an abbreviation for light. There's a formula that allows you to calculate the energy of light. It's the energy equals Planck's constant times the frequency. And so HV is an abbreviation for this constant times the frequency. It's just a way of showing light is used to provide the energy for this reaction. And when light's used, it almost always breaks bonds homolytically. We don't see light breaking bonds heterolytically nearly as often. So what's happening here is these two chlorines are bonded. The energy from the light hits the electrons, and they absorb the energy and become a higher potential energy state, forming free radicals. So when that light hits the chlorine, that happens. You could also imagine the light hitting the carbon-hydrogen bond. So if the light hits that bond, it could also break homolytically, which would produce a couple free radicals. So you might be thinking, well, why doesn't that occur? Oops, that should be a hydrogen. Well, that could also occur. It's just not going to occur nearly as often when we look at the energies. Right? So if we look at the energy required to break the chlorine-chlorine bond versus the energy required to break the carbon-hydrogen bond, it's significantly more. So much more often, the lower energy pathway is going to occur. So because of the energies, the activation energies here, and the kinetics involved, carbon-hydrogen bonds don't break nearly as often. The energy required here is about 400 kilojoules per mole versus chlorine, which I think is about 260 kilojoules per mole. All right, so the chlorine breaks, that starts to process off and produces this chlorine radical. That doesn't need to happen very often. It also doesn't need to be very product favored. All that needs to occur here is a few of these radicals to form. Once they form, they might just join back together and go back to the reactant site. So you'd probably continue hitting it with light to ensure that most of the chlorine molecules that exist there have the opportunity to break apart to form at least a few radicals. Once these radicals form, though, the radical can do a hydrogen abstraction. So it'll pick up an electron and the hydrogen to form HCl, leaving one electron behind on the carbon. And that's pretty unstable because the carbon is a relatively small atom. The smaller atoms don't deal with instability as well. They don't deal with incomplete noble gas configurations or formal charge as well. It creates more of an instability. So that carbon's likely to pick up a halogen and regenerate the chlorine radical, which then goes back up here and collides with another methyl group. Right, so these collisions produce the same reactant. It's not a reactant, but the same species that was produced initially when the chlorine underwent homolytic cleavage. So every time this occurs, it produces another one of these chlorine radicals that can then start another propagation step series. And so when you think about the word propagation, what we're referring to here is specific steps in the mechanism that are responsible for the vast majority of the product formation. Right? That first step is necessary from this slide over here, the initiation step, it's necessary, but it doesn't have to happen every single time the product is produced, because once the chlorine is produced, these two steps can self-sustain one another and continue over and over again, because they always produce something that goes back with another methyl group and continues the process forward. So what is the actual definition of propagation? So there's a few criteria that have to be met for steps to be part of the propagation process. And one of those is for the sum of the propagation steps have to equal the overall reaction, balanced equation for the overall reaction. And so that's what's happening here. If I cancel everything out that appears exactly the same on both sides of the arrows, what I end up with are the exact reactants and the exact products in the overall reaction. So that's criteria one. If I'm going to claim these two steps are propagation steps, then the sum of these steps, once everything's canceled, has to give me the overall net reaction. Criteria two is that they are self-sustaining. As we said, the two propagation steps work in tandem, where the second one produces what I need to be available in the first one to keep them both going. So I don't need any other steps to produce product here. All I need is these two steps, because they continue to produce more chlorine radicals, and that can pretty much use up all the methane and convert it all into product. And then sometimes termination steps occur. As we said, these are not very common, specifically because the concentration of radicals in solution is very low. And so typically when a radical forms, if it's a chlorine radical, it's much more likely to bump into a methane molecule. Or if it's a methyl radical, it's much more likely to bump into a chlorine molecule. Right? The radicals are not very high in concentration, so they just don't collide with one another very often. But once in a while they do, and when that occurs, a termination event happens, which combines usually radicals together and stops the process from continuing. This one is going to be especially uncommon because the methyl radical is especially unstable. There's no hyperconjugation or resonance to stabilize it, so the amount of it present at any given moment is going to be quite low. And so the odds that two of these would meet up would not be happening very often. So as we said, propagation steps must be self-sustaining, and the sum of the two propagation steps added together have to give the net reaction. And they're self-sustaining specifically because the chlorine radical that's generated in the second step is what's needed to do the hydrogen abstraction in the first step of the propagation. So these two parts are the propagation parts. All right, so there's an issue with this reaction that we have to discuss. The reaction is difficult to control. So what we just saw was the mechanism by which methane can be converted into chloromethane. The problem with that, though, is that once chloromethane is produced, it still has hydrogens. If I want a clean reaction where 100% of these molecules all get converted into one product rather than a mixture of products, I could think about using a 1-to-1 mole ratio of my two reactants. But as soon as some of this reactant is converted into the product, it's possible that the remaining chlorine can start reacting with the product. So we want to take a look at this process by which multiple substitutions can occur and try to understand why this is so difficult to control. So what's happening here is, in the mechanism we just showed again, the methane molecule reacts with chlorine radicals, right? So first, the two chlorines, since their bond energy required to break that bond is less than the CH bond, that will break and produce radicals, produce two of them. But one of those radicals will then abstract a hydrogen, as we showed, to produce a methyl radical. That's relatively unstable, so that's going to pick up a chlorine. Now, what students have a real tendency to do is at this point to have the chlorine as a radical and just join together. Because if the chlorine and the methyl join together, I form the product that I'm expecting to see in this reaction. But as we said, the quantities of radical in solution are quite low, so it's very rare that they actually meet up with one another. So that's not the best way to show the mechanism. Instead, the methyl group is much more likely to collide with the chlorine, right? These are more stable, they have complete noble gas configurations versus the free radical. So when this collision occurs, if enough energy is present, the methyl will pick up an electron and a chlorine, and the other chlorine will pick up the other electron, and you'll get a regeneration of the chlorine radical. Right? So these are the two propagation steps that form the majority of the product. So if I have 100 molecules of these, obviously I'd have a lot more than that if I were doing a reaction at a laboratory scale amount, but just for the sake of argument, if I had 100 of these, after the first few start to produce this product, maybe I'm forming now, maybe I have 5 of these, and I only have 95 of these. It's still, since I have so much methane, it's probably more likely that the methane will collide with this chlorine radical that's regenerated or one of the other ones around. But once a significant amount of this starts to build up, it can also react with a chlorine radical through the same reaction. The hydrogen abstraction can occur, leaving an electron here on the carbon. And if I want to look at the energy required to do that, I want to compare the two pathways. Right? So we'll call this pathway A and this pathway B. Pathway A goes through a methyl free radical. That second step is pretty unstable. So as that occurs, as that methyl free radical, actually that's the product of the first step. I apologize. The first step is the slow step there, because forming a free radical on a small atom that's not stabilized by hyperconjugation or resonance, that requires a fair amount of energy. So for pathway A, that first step requires a significant amount of energy. For pathway B, since the radical I'm forming here is stabilized through resonance with this chlorine, to form this resonance contributor. And so it's a little bit unstable on the chlorine because the chlorine has more than 8 valence electrons, but since it's a third energy level atom, it can hold more than 8. So these two resonance contributors are similar in stability, and that stabilizes the free radical, right? So a free radical on a carbon that has a chlorine attached, or really anything with lone pairs, that's third energy level or below, is going to stabilize the free radical more than just a methyl. So once a small amount of this starts to build up in solution, it's more likely to react than the original structure because it will go through a lower energy pathway and produce a more stable carbon-free radical. So it's just going to happen more often. And so I can't control this process. Once another chlorine's attached, even more resonance will stabilize it. So attaching more and more chlorines is favored by the molecule, and you really can't stop it from occurring. So if your goal is to substitute all the hydrogens for halogens, then you just use excess halogen and you keep heating it up and you wait for it to do it on its own. If your goal is to convert 100% of the molecules into one product and only replace one hydrogen with one halogen and not continue to replace hydrogens with more halogens, this is not going to work for you. So we want to take a look at some other halogens in addition to chlorine after we do a full analysis of this reaction. So instead of methyl, maybe I've got this isobutane molecule, which is also known as 2-methylpropane. So what would happen here? Well, here I've got different types of hydrogens. Potential regiochemical outcome is different here if the chlorine picks off the middle hydrogen versus one on the outside. And so again, the chlorine is going to first be hit by the heat or light to produce chlorine radical. And then the question is the chlorine radical more likely to collide with one of these outside hydrogens or the inside one? So if there were no stability difference, and we're just looking at the statistical likelihood of a collision occurring, well, since there are 9 hydrogens out here total that are all equivalent on the outside, it'd be much more likely for the chlorine to react with one of those. And so let's take a look at what that would produce. So the chlorine would abstract a hydrogen, leave an electron behind on the carbon. That would produce a primary free radical. But primary free radical is not very stable compared to a tertiary. So the chlorine could also pick off the hydrogen from the tertiary position and leave an electron behind there. That would create a tertiary free radical. So statistically, there's 9 times more likelihood that the chlorine would go to the outside. But in terms of the energy diagram, the energy of the reaction that goes through a primary free radical is going to be higher in energy than going through the tertiary free radical. So by that logic, since only the strongest collisions would have the energy necessary to get to the primary free radical transition state versus the tertiary one might happen more often. So that's going to produce potentially a mixture. If the chlorine radical is fairly unstable, it might react anywhere. It might produce both of these. And so that's why we're kind of seeing a mixture of products. So if the tertiary free radical does a halogen abstraction, it would produce this product. If the primary free radical does a halogen abstraction, both of those regenerate another chlorine radical to continue the process forward, but here the chlorine would attach to the primary position, and that would give this product. And then as we said on the last slide over here, we can't stop it from doing multiple chlorinations. So that would also potentially produce chlorines at both positions in a few of the molecules. So I would get a mixture of a variety of different products. This one would be very minor. It would only result when the primary radical and the tertiary radical both form on different molecules and last long enough before they react with anything else and then join up with one another to combine together to form this new sigma bond between them right here. That wouldn't happen very often, but it might happen a little bit. And so that also complicates the situation a little bit. So while this might be the most major product because it goes through the lower energy pathway, and these two might be a little bit more minor, I'm getting a mixture of products, and that's a problem for me synthetically. Why do I want to install a halogen on a hydrocarbon? Well, hopefully, from what we talked about last semester, that's obvious to you. And if I just have hydrogen and carbon, we didn't learn any reactions last semester that will work on these molecules. So this is the first time we're talking about a reaction where it can actually react to hydrocarbon with no pi bonds, just all sigma bonds. It's pretty stable. So the goal here is to convert this, to do a synthesis where I can convert this molecule into 100% of maybe one product that I want to make. And by replacing a hydrogen with a halogen, Now I have a leaving group, so I can do other reactions. I could do an elimination reaction, I could do a substitution reaction, etc. So that's the point here. This reaction is not going to work very well because it produces a variety of products. A couple other points that we want to make today about halogens, about free radicals, is some other initiators that you can start with. So as we said, the chlorine bond is relatively unstable. It doesn't take a huge amount of energy to break it. But oxygens, being even more electronegative, put even more tension on the bond, so even less heat or light energy is necessary to break that. And then if the resulting radical can be stabilized through resonance, it takes even less energy. And so once we get down to a bond energy this low, now we're in a practical area where we can actually use heat to break that bond without having to heat it up so high that everything else starts to break down and decompose. So the importance of initiators that will produce radicals very readily is we can start radical reactions with these type of initiators at reasonable temperatures that are common for a lot of organic reactions to take place at. Another important consideration, and we'll talk more about this in the future as well, is the presence of oxygen can really mess up your reaction. So normally we think of oxygen as existing as a molecule, and it looks pretty stable. There's no formal charge. All the noble gas configurations are complete. But if a certain wavelength of light, maybe cosmic radiation, X-rays, gamma rays, ultraviolet light coming from outer space, and come in here and hit this bond, or if enough heat is involved, the pi bond here, which isn't as stable as a sigma bond, can break homolytically. And that produces a diradical. It's a diradical because there are two radicals on the same structure. Once this occurs, it's very reactive. It's likely that the electrons will move back in to reproduce the O2 molecule, which is then stable again, but they might not necessarily rejoin. Instead, this radical might undergo one of the patterns we talked about. It might abstract a hydrogen from somewhere or start reacting with pi bonds. So oxygen is often a culprit that causes undesired side reactions. So a lot of times we want to modify a reaction to stop oxygen from getting involved and causing some undesired side reaction or inhibiting our self-sustaining chain reaction that we're trying to use to convert reactants into specific desired products. So there's a couple different ways you can stop oxygen from getting involved in reactions. One is to eliminate it from the reaction altogether, and that would involve using a vacuum to remove the air and then backfill the reaction vessel with nitrogen gas, because nitrogen doesn't do the same thing. Nitrogen is way more stable and inert. It's a great atmosphere for reactions to occur uninhibited or not involving oxygen to affect them. Excuse me. Another option is to use a radical inhibitor. So if oxygen forms this unstable diradical form, and it starts reacting with a carbon-hydrogen bond or something like that, it could pick off this hydrogen and leave behind an electron and form a carbon radical. And this is a pretty unstable diradical, so that can happen anywhere on the structure. And so that could result in a variety of side reactions. So the idea here is we want the structure to go back to its original form, because that's the substance we're trying to create or work with. We don't want it to form a radical. And this is especially important in food spoilage. And so if your food is likely to get spoiled, you might keep it in a container that's dark. It's got brown glass, or maybe won't allow light to penetrate into the container, because light and oxygen can cause these free radicals to form, and then they can react with the oxygen and produce rancid, spoiled food. So preservatives work this way. Hydroquinone is one of them. It's often added to chemicals to prevent them from reacting with oxygen, because when the chemicals react with oxygen to produce a free radical, a carbon free radical, which is represented by R here, this molecule has two hydrogens it can sacrifice to convert the carbon radical back into the original hydrocarbon structure. And so that works where the carbon radical picks up a hydrogen and produces an oxygen radical. Now this one's stabilized by resonance with the ring, right? It can move in here, this can move out here, and the electron, the free radical, can be stabilized in multiple positions around the ring. So that's good. That's stable enough to just kind of hang out like that. If it happens again, though, and there's another undesired carbon radical, that carbon radical can pick up another hydrogen, abstract another hydrogen, and form another free radical. And then those free radicals will combine in this way, producing benzoquinone, which is no longer a radical. So by sacrificing both of those hydrogens, the hydroquinone becomes much more stable as a structure. And so basically it just provides hydrogen and an electron to join up with the carbon, so that we don't get these random carbon free radicals forming, causing a bunch of side reactions. So sometimes this is added to chemicals that are going to be stored on the shelf for a while if they're especially susceptible to reacting with oxygen. All right, so then the last section for today, we're going to talk about some of the thermodynamics of these halogenation reactions. And this is going to set us up for a more complete discussion of the thermodynamics that we're going to talk about on Wednesday. So if you recall, thermodynamics is all about products versus reactants, right? If we're interested in thermodynamics, the question is this reaction going to produce more products when it gets to equilibrium, or more reactants? Which side is favored when equilibrium is reached? Right? Thermodynamics does not tell us about how quickly a process will occur. It doesn't tell us about the activation energy, which step is a slow step, or really anything about the mechanism. It just tells us overall, if we compare the free energy of the products versus the reactants, which one is favored, or which one will we have more of when it reaches equilibrium. So if you recall, we know that for delta G, if it's negative, that's spontaneous or product favored. If the standard free energy is negative, it's going to be product favored. Alternatively, if the free energy change under standard conditions is positive, it's non-spontaneous, which means that it's reactant favored. So if we can figure out the sign for delta G for reaction on paper, then we don't have to worry about running it if it's not even going to give us a product favored situation. If we want to make a product, we want to make sure our reaction can actually give us a significant amount of it when it reaches equilibrium, otherwise it's probably not worth doing. So we know if we're going to try to determine the sign for delta G, we want to look at delta H, we want to look at delta S, and think about how the temperature might affect things. So let's take a look at delta S first. What should the sign for delta S be in this reaction? So if we want to look at the halogenation of a hydrocarbon, where a hydrogen is substituted for a halogen, so that we can then use that for some subsequent reaction where maybe the halogen acts as a leaving group. we want to think about the entropy change for this process. Recall that entropy is about variety. It's about how many different ways particles can be positioned and moving around in space. So when I've got 2 total moles of reactants, 1, 2, and 2 total moles of products, 1, 2, how can I tell which side has more entropy? Well, maybe one side has a little bit more vibrational or rotational variety. I really can't tell by looking at it, and even if one side did, it probably wouldn't be by much. So anytime you have equal numbers of particles or chemical units on both sides of the arrow, you can expect them to have really similar amounts of entropy. And so if we want to look at the change in entropy by comparing the products versus the reactants, if they have similar quantities of entropy, because we have equal quantities of moles of substances, when I subtract, I should get a value that's pretty close to 0. So delta S here, I can't really tell if it's negative or positive, but either way, I know it's going to be a very small value, pretty close to 0. And if I multiply a very, very small value, whatever the temperature is, it's still going to end up with a very tiny entropy term. And subtracting or adding a tiny value from delta H is not going to affect it very much. So anytime delta S is close to 0, this term becomes very small, and adding or subtracting it means it's not going to have any impact on delta G. So I can really just drop it out entirely and take a little shortcut here and recognize that delta G is only going to really be impacted by the value for delta H. So what we're doing here is we're using delta H as a proxy for delta G. Because the T delta S term is so close to 0, the sign and value for delta G should be very similar to delta H. And that allows the analysis to be much simpler because we know the bond dissociation energies for all these bonds. And we can figure out how much energy is it going to take to break the initial bonds. Those will be positive values. And then how much energy it's going to take, or how much energy is going to be released when the new bonds form. Those will be negative values. So by adding up the energy absorbed and subtracting the energy released, we can calculate the total enthalpy change for each of these reactions, and each of these should be very similar to delta G. And so what that means is, when I react a hydrocarbon with fluorine, it's highly exothermic, also exergonic, right? The thermic is H, the G, exergonic means it's product favored. So this looks like a nice reaction, very product favored. The other two also look product favored here, but the reaction with iodine is actually reactant favored. It's non-spontaneous. It's not going to produce more product than reactant. It's actually going to go back mostly. So that means it's not very practical. I can't make mostly product if my reaction favors the reactants. In terms of the fluorination reaction, it's actually too exothermic. That makes it unpractical. One, because it maybe releases more heat than can be controlled. But two, it's completely non-specific. As we were saying, it's hard to stop the reaction after one halogen replaces one hydrogen. But when the halogen is fluorine, it's really impossible. I can't control which hydrogen the fluorine replaces, and I can't prevent it from replacing all the hydrogens. So if my goal is to take all these hydrogens and replace them all with fluorines, then this is going to be fine. I just have to be careful safety-wise, because fluorine gas is extremely toxic and dangerous, and hydrofluoric acid is also dangerous because it will eat through glass or dissolve glass, which means I need to use plastic materials instead of glass. But if I take the proper safety precautions, I can convert a hydrocarbon into fluorinated hydrocarbon. I just can't stop it from replacing all the hydrogens with fluorine atoms. So those two reactions, as far as organic synthesis goes, are not as useful. If my goal is to replace one hydrogen with one halogen so that I can use that to do some other substitution reaction or whatever and build up the complexity of my structure in a controlled way, fluorine and iodine are not going to be my go-to. So that leaves chlorine and bromine to look at in more detail. And as we said prior, it's the propagation steps that form the vast majority of the product. Because they're self-sustaining, the second step produces a substance that's used in the first step, and so that can go back and continue the reaction over and over and over again. So the propagation steps that produce most of the product, those are the ones we want to focus on if we're trying to decide whether chlorine or bromine makes more sense to try to specifically replace one hydrogen with one halogen. If we look at the overall entropy change, the overall enthalpy change, which is going to be similar to the overall free energy change, they're both exothermic, which means they're both going to be exergonic or product favored. That's good. But the key thing we're really interested in synthetically is how do we control this? How do we get one hydrogen to be replaced and not all of them? And how do we control which hydrogen it is? Right, so we're going to talk about that a lot more next time. I just want to set you up for that discussion because there is a difference in how these diagrams look, which can be used to explain the results of the reactions, which is what we're going to do next time. So just to go back, note that when I'm using chlorine, both steps release energy. So when chlorine is involved, the first step releases a little energy, and then the second step releases energy. So they're both exothermic, they're both exergonic. There's a small activation energy, so this reaction occurs pretty readily. When I'm dealing with bromine, though, the first step is actually endothermic and endergonic. And the second step is exothermic and exergonic. So what that means is for bromine, the first step, I have to put energy in to get to the intermediate, and then the next step, energy is released. So overall, delta G is negative, which means it's going to be product favored overall, but the first step is not product favored. And we're going to see the consequences of that in detail next time. So let's just answer these questions, make sure we're all on the same page before we end. So which step is the slow step? The slow step is always a step with the highest transition state energy. Not necessarily the highest activation energy, although in this case it's also the highest activation energy. The first step here actually looks like it has about the same activation energy as the second step almost. The key though is that it reaches a higher total energy point in the transition state of the first step than in the second step for sure. So the first step is a slow step. Likewise here, the first step reaches a higher total energy point than the second step. So the first step is a slow step. And that's going to be important when we're talking about the kinetics, right? When we talk about kinetics, the slow step helps us recognize what is really determining the overall rate at which this reaction occurs. Second question, which reaction has a faster rate, the chlorination or the bromination? And obviously the chlorination, right? That's determined by the activation energy. Almost any even weak collision will probably have the energy necessary to get over this transition state and make the products. But when bromine is involved rather than chlorine, since the first step is endergonic or endothermic, that means that not very many collisions will have the energy necessary to get up there. So this is maybe starting to give you a hint about why bromination is favored synthetically. If only the reactions that have just enough energy to get up there occur, I maybe have a little bit more control over which reactions occur. Here, any reaction with chlorine is going to be fast, so it's hard to control the process. We'll see that in more detail next time. The chlorination, though, is more product favored. Right? So if we're looking at how product favored something is, that's going to be determined by the value for delta G. And overall, for chlorination, for from the starting value to the end, that's a big negative delta G. For bromination, from the starting point to the end, it's still a negative delta G, it's just not as big. So this is more product favored than the bromination. But what we're going to see next time is the bromination is more selective because we can exploit this fact that this first step is endothermic to only put enough energy in to go through the lowest energy pathway and not higher energy pathways, which we'll see in more detail next time. So to prepare for the first exam, which is going to be next week, I believe the first exam, I'll check the syllabus on this, but I'm pretty sure it covers day 1 and day 2. So you want to be prepared to answer questions related to any of these bullet points, as well as the bullet points on day 2, which obviously we'll talk about day 2 on Wednesday, which is day 2. Also, to help you practice the skills for what we just talked about in this lecture today, I recommend you look at these practice questions from the textbook, and the solutions guide can help you make sure that you are answering those correctly. And if you have questions about any of that, please let me know anytime. And then to prepare for day 2, which is on Wednesday, I recommend that you check out these videos. And there's a couple other helpful ones, as well as reading the sections. We covered 11.1 through 11.4, but the rest of that we're going to talk about on Wednesday. So to make the most out of that lecture, you definitely want to read those sections, work on some of the practice questions within those sections, and watch the suggested videos. As we were just saying, we're going to look more at chlorination versus bromination, and in a lot more detail. So you want to be relatively familiar with that. All right. I hope. Just one other thing, just to point out, if you're not aware, in our Canvas course, if you scroll down, you'll see the lecture videos posted here, but in addition, you can also see the bullet points and practice questions from the textbook, the same ones we just saw in the PowerPoint slides, as well as the same day 2 prep materials, the same videos. If you want to watch them within Canvas, you can, or just go to the links, and that also shows you the sections of the textbook to read for the next class, so you don't have to actually open up the PowerPoint to look at that content. All right. Bye, everybody.